In Gases 6, I'm going to talk to you about vapor pressure and partial pressure. Now, a vapor pressure can be defined as the pressure exerted by the vapor of a substance, and it depends on what the substance is, in other words, the chemical structure of the substance, as well as the temperature of the substance. Let's take a look at a schematic diagram to help conceptualize this idea. On the left, we have a substance at temperature 20 degrees Celsius. On the right, we have the same substance at a higher temperature. Well, you should notice that on the right, those particles have more energy. They have more energy because they're at a greater temperature. And we've talked about this several times in previous units. So as temperature increases, so does the kinetic energy of this substance, which means these molecules on the right have enough kinetic energy to escape the liquid form and turn into a gas, which means they have enough energy to break the intermolecular forces that exist among them. Let's look at another diagram. Here we have another liquid, and in this apparatus here, you can see it is composed of a column, and in that column is a substance. Now, if we compare the column on the left to the column on the right, we can see that the column on the right has a greater vapor pressure, which is measured as a distance between this liquid, say mercury. And the reason why is the substance on the right has more gaseous particles. Now recall what that means. In both instances, this one here and this one here, because there's more gaseous particles, there's more collisions with the vessel, and that is creating a greater pressure within the vessel over the liquid substance. That is what vapor pressure is. Let's look at a graph to help us understand that. Here we have the number of molecules as a function of their kinetic energy. Now, specifically, we're looking at the number of molecules with a particular threshold of kinetic energy. That kinetic energy being the amount of energy needed to escape the liquid form and turn to a gaseous state. We have temperatures of 300 and 400 Kelvin. Well, what you can see at this threshold here is that in green, which is the molecule at a higher temperature, in green it has a greater kinetic energy. What does that mean? Again, it means they're moving faster, and so because of that, they're able to break the intermolecular forces and turn from a liquid state to a gaseous state. Now, compare that to the graph at 300 Kelvin, and you can see in purple, there's a smaller fraction of molecules that have that particular threshold of energy. Now, you may be wondering what this symbol is here. That is E naught. Now, E naught can be defined as the minimum amount of energy that is required to overcome the intermolecular forces. And so again, that minimum amount is what I'm referring to as that minimum threshold, and we call that E naught. Another point that should be made here is I am going to give you a handout here that'll go in your notebooks, and it is the water vapor pressure. So this particular table is specific to water, and in some upcoming labs we're going to be collecting gas over water, and so because we have a vapor pressure exerted by the water, we need to compensate for that, and I'll explain this in more detail a bit later. So let's talk about what the boiling point means. What does it actually mean for a substance to be at its boiling point? Well, it means that the temperature of its vapor pressure is equal to the pressure of the atmosphere. So let's take a look at this table here and make some comparisons. Let's start looking at 0 degrees Celsius and compare that to the corresponding pressure in kilopascals. We see at 0 we have 0.61 kilopascals. And now let's compare that to 100 degrees Celsius, and we can see we have 101.3 kilopascals, which I'm sure by now you recognize as the pressure at standard temperature and pressure, or STP. So at this temperature of 100 degrees Celsius, which we know at sea level is the boiling point of water, well, that equals a vapor pressure that is equal to the pressure at STP. Okay, let's compare the boiling point and atmospheric pressure at different locations in the world. This is pretty cool to look at this. Let's start by looking at Mount Everest. On Mount Everest, water will boil at 70 degrees Celsius. We'll look at the altitude above sea level on the summit of Everest. So what's happening here is at the summit of Everest, there's a much lower atmospheric pressure. Because of that, atmospheric pressure being the pressure exerted onto the liquid, in this case water, is less. If there's less pressure exerted downward onto the substance, then that means more can escape and turn into a gaseous state. And that's going to occur at a lower temperature than, say, STP. Let's look at Washington, D.C. Washington, D.C., we're at sea level, and water boils at 100 degrees Celsius, just like what we're used to. And then lastly, the Dead Sea. This is pretty cool. Dead Sea is below sea level. So there's a greater atmospheric pressure exerted down onto the water, the liquid water, which means it requires a much higher temperature for water molecules to have enough energy to escape into a gaseous form. Now let's look at these 4 different substances. Let's compare their vapor pressure and corresponding boiling points. We can start with water, and at 25 degrees or room temperature, it has a vapor pressure of 2.3 kilopascals. Now, and that corresponds with a 100 degree Celsius boiling point. So now let's compare that to diethyl ether, which is an extremely volatile substance. Dimethyl ether has a vapor pressure that is much greater. Okay, now remember what that means. The vapor pressure is when they've escaped into a gaseous state and they're exerting pressure down onto the liquid. And it's to help you conceptualize that, I showed you a couple schematic diagrams at the start of this video. So diethyl ether's boiling point is only 34 degrees Celsius. Let's get a definition for volatile. These are defined as liquids that have high vapor pressures, and thus they will evaporate easily, okay? And the best example right here would be diethyl ether. And of course, we could rank these substances as their amount of volatility. However, one thing I usually associate volatile substances with is you can smell them. So like gasoline and alcohol is volatile. And that's because they are able, again, to escape from their liquid form and turn into a gas, comparatively speaking, when we look at, say, water. And lastly, let's look at mercury. Has a very low vapor pressure, and that should make sense. Because of its extremely low vapor pressure, we see that it has an extremely high boiling point. So it takes a great raise in temperature for those particular molecules to reach that threshold to turn to a gas. At a pressure greater than 1 atmosphere, water boils at a temperature greater than 100 degrees Celsius. I hope that's intuitive at this point. Let's look at another graph to help us understand that. As you know, for this particular topic, our Georgia Standards of Excellence ask us to look at this conceptually, mathematically, and graphically. So here's a graph of the vapor pressure as a function of temperature in degrees Celsius. And we see here a number that is hopefully very familiar, 760 torr, which is equal to 760 millimeters of mercury, or 1 atmosphere of pressure. Okay, so at this standard pressure, we are given the corresponding temperatures here, as you can see, and the corresponding vapor pressure. Now, what that's telling us is when these substances will boil, and you can see here that, again, diethyl ether has this very low boiling point, which means it has a high vapor pressure, and then we can compare that to water. So we've looked at this now graphically as well. Increased pressure, again, forces those molecules on the surface to condense. In other words, molecules must have enough kinetic energy to escape, and we called that a threshold, or E naught, that minimum amount of energy required. And we've also seen this animation before of a substance having enough energy to escape into the gaseous form, all right? But increased pressure is going to lead to an increased boiling point. So think back about comparing the Dead Sea and the boiling point of water to a location on planet Earth, the summit of Everest, that has a very low atmospheric pressure, and thus water boils at a much lower temperature, a mere 70 degrees Celsius. All right, now we can talk about partial pressure. John Dalton's empirical law of partial pressures is very intuitive. However, it can get a little complicated later on in this course, and especially in AP chemistry. But it states that the total sum of pressures exerted by a mixture of gases is the sum of the partial pressures of the individual component gases. Okay, so let's look at this schematic diagram here where we have a pressure of helium, nitrogen gas, oxygen gas, and all of those are at standard pressure. So if we look at the total pressure here of these, we're going to simply add. It's the total pressure of the mixture. 1 plus 1 plus 1 is 3. And I know what you're thinking now. You're thinking, wow, this is incredibly simple. Okay? And the idea is, as long as you can keep it straight as we move forward, we're going to be applying this to the ideal gas law and looking at mole fractions of gases, etc. Okay, so this mathematically can be expressed as the following. And if you are not familiar with this symbol here, this is the summation symbol. And what it's telling us is the sum of these quantities, and we're going to start with an integer of 1, and we're going to go to n. So we're going to keep going until we're done. So in the case of our schematic with our gases, in would go 1, 2, 3. So it would keep going until we reach the total number of gases in the mixture. And of course, this is showing the pressure starting at our first integer of 1. Okay, so that's what that all means there. Keep in mind, this handout, this little table that you're going to tape into your composition notebook, this table gives you the vapor pressure. So we're going to need to account for the vapor pressure of water if it is indeed part of a mixture of gases. And this is cool because we're coming up to a lab that I really enjoy doing, where we're going to be essentially collecting a gas over water. More on that coming up. Now, let's do a practice problem. Two gases are combined and sealed in a 2-liter container. The 3 liters of argon and the 1 liter of xenon each exert 1 atmosphere of pressure on the walls of their individual containers. So we want to calculate the partial pressure of each gas, but in the new container, the 2-liter mixture. So we have 2 gases in their own respective containers. However, they're going to be combined and sealed into a container that is 2.0 liters. So let's think about how we're going to do this here. We have pressure and we have volume. And so what we could look at here would be Boyle's law. And this is that inverse relationship that compares pressure and volume. Let's first start by looking at argon. Here at 1 atmosphere, in a 3-liter vessel, we have are able to equate that to pressure 2, but in a smaller vessel, a 2-liter vessel. Let's get a number for that. Rearranging and solving for P2, we get our new pressure in the 2-liter vessel to be 1.5 atmospheres. Okay, next we're going to look at xenon, and we'll use Boyle's law again. So we have at 1 atmosphere in a 1-liter vessel, and we're going to calculate the final pressure of xenon in a 2-liter vessel. Mathematically rearranging this, we get the new pressure in the 2-liter vessel equal to 0.5 atmospheres. Now we're going to apply Dalton's law of partial pressure, and we're going to solve this to say the total pressure in the 2-liter vessel is 2.0 atmospheres. Let's do one more here. Here we have a cylinder of a compressed natural gas in 20-liter volume, and it has a couple gases in it. It has 1,813 grams of methane and 336 grams of ethane. Calculate the partial pressure of each gas at 22 degrees Celsius and the total pressure of the cylinder. First things first, you know we're going to need to get this into mole. You know we're going to use molar mass. Let's go ahead and do that. So there are 16.04 grams of methane in 1 mole of methane. That gives us 113 moles. All right, it's all about the mole. We need the mole if we're going to calculate anything about the gas. Let's use the ideal gas law now. Let's put in what we have and rearrange for pressure. We now know the moles. We know the ideal gas law constant. In fact, we derived that in previous videos. And we know the volume. We need to make sure our volume is in liters. Our temperature is in Kelvin. And we can rearrange this and solve for the pressure of methane gas to be 137 atmospheres. So you can see how Dalton's law of partial pressure, it adds an additional component to what you need to think about when dealing with gases. Let's look at ethane. 336 grams of ethane. Let's use dimensional analysis and the molar mass of ethane to calculate the moles of ethane. So we can know there are 30.07 grams of ethane in a mole of ethane, and thus that equals 11.2 moles of, that should say, ethane. Okay, so this here should say ethane. No worries. Moving on. Let's use the ideal gas law and rearrange the ideal gas law to solve for the pressure of ethane. And the pressure of ethane is going to be 13.6 atmospheres. So this one, a little different. We had some more variables. We had to use the ideal gas law. We had to use the fact that we were given grams, so we had to do a one-step mole conversion using the molar mass. And now what we need to do is apply Dalton's law of partial pressure by summing the partial pressures of the component gases to get our total pressure in the cylinder is equal to 151 atmospheres. Our Georgia standards of excellence, we're again looking at pressure. We're going to take pressure, we're going to convert it and look at the number of moles of a gas, and we use mass to mole computations to accomplish that. I'll see you guys in class.